I'm Luke McKinney, Prep 101's Civ 100 instructor, and in this video we'll be talking about forces, the basic forces that'll be contributing to problems all the way through the course, especially trusses and frames machines.
Forces. A force is normally anything that can cause an acceleration. So you add up all the external forces acting on something and you get the mass times its acceleration. But not in an engineering statics course like this. If you build a bridge and it suddenly starts accelerating, well, you have made a mistake and you're going to be getting a lot of very angry letters from pretty much everyone for the rest of your life. So what we do is we deal with equilibrium, where the sum of all the external forces on something is zero. And that is equilibrium, where the acceleration is zero. And that's honestly half of all the equations you'll need for several problems this year. The other half will be moments pretty soon. So this equation alone lets us deal with certain problems. For example, if we have a structure, let's say we have a bridge here, and we've 200 Newton force pushing to the right, and we've some unknown force A pushing to the left. What have we got? Well, we know the sum of all the horizontal forces acting on that must be zero. We draw our axes so we know which way is plus. We usually take x as positive to the right and y is positive up. So the sum of all the horizontal forces here, we have 200 newtons going to the right, so that's plus 200. And we have A pushing to the left, so that's minus A is 0. And so we find A is also plus 200 newtons. Now remember, that plus means it's in the direction of the arrow we drew at the start. So it's to the left, as we'd expect. Remember, in engineering, plus and minus are just directions. If you draw something with an arrow, plus means it's in the direction of that arrow, minus means it's opposite. And this is the guts of a lot of the problems you'll be facing this year. Sometimes you look at a whole structure, sometimes you look at a piece of a structure, but you still have forces that must all add up to zero, and you can solve them. Of course, they're not usually going to be one-dimensional like this. We must learn how to deal with two-dimensional forces. So how do we do that? Well, if we have a force at an angle to the horizontal, we can break that up into a horizontal component and a vertical component using trigonometry. The horizontal component of the force is the force times the cosine of the angle, because it's adjacent to that angle. And the vertical component is the force times the sine of the angle, because it's the opposite side to the angle. If you're rusty on your old trigonometry, the SOHCAHTOA, do make sure to have a wee look at that. But a more important thing here, I want to get this in right at the start of the year with you. You'll notice what I said. I didn't say fx equals f cos theta, because that's an override code for a terminator or something. That's not how people speak. What I said was the horizontal component of the force is the force times the cosine of the angle. And you'll find if you say the words as you go through these problems, you'll actually gain a lot more understanding. You'll be able to connect them to the problems much easier. Whereas if you just read out all the letters, it looks like you're gargling a bag of Scrabble tiles and cheating, because stuff like theta isn't in regular Scrabble. And once we have these angles, then we have pretty much everything, and we can do more equilibrium problems. The first thing we do with any such problem is a free body diagram of whatever piece we're looking at. Sometimes we're looking at the whole thing, the whole structure. Sometimes we're looking at a chunk of the structure or just one piece of the machine or frame. That's like 60% of the course, but it's all based on the same idea. The free body diagram is you just draw the object and the external forces acting only on that object, not on any other pieces that aren't in your diagram. So if we then have some forces acting on that, so let's say we have 200 newtons pushing to the right. We have the force A at 45 degrees like that, and we have the force B pushing down. Now you'll notice here something about the forces. It doesn't matter where on the body the forces are. As long as they're on the body at all, you can add them up like this. And so we're going to go through this. We draw our little axes, so we remember which way is which. Y is up positive, X is to the right positive. So then we just do them. So we can choose the X-axis or the Y-axis to look at. You might default to doing X first, and that always works well, but you can save a bit of time if you look at it and think, well, hang on, which has the fewest unknowns? Here we can see only one of the unknowns has an X component, whereas two of the unknowns have a Y component. So yeah, we do X first, but if you do that little check first, you'll sometimes find it saves you time. So I wanted to give it to you right here in this first lecture. So let's look now. The sum of all the horizontal forces is 0. So I have plus 200 pushing right minus the X component of A pushing left. That's one equation with one unknown. So it's A is 200 over cos 45 is 282.84 newtons. And then we move on to the next one. The sum of all the forces vertically in Y is 0. So we've minus B pushing down plus the Y component of A. But we know what A is, so we've minus B plus 282.84 times sine of 45 is 0, and we find B is 200 newtons. Now remember, that's positive, so it's in the direction of the arrow. In engineering, plus and minus are just directions. It's plus, so it's in the direction of the arrow there. Because remember, we'd included that down when we put the minus there. If the answer ever comes out negative, no problem. You just say it's in the opposite direction to the arrow you started. So we've broken vectors up in order to solve problems, but let's say we've got those components at the end of a problem and we want to add them back up together to find our vector again. So let's say we'd found some resultant vector, the X component, by adding the components of other vectors, and likewise the Y component. And now we wanted to put those back together to find the resultant vector. Well, the way you do it, we have an X component and a Y component. So we can find the size of the vector by Pythagoras. So the size of the vector by Pythagoras is the square root of the sum of the squares of the other two sides. And then the angle by trigonometry is the inverse tan of the opposite side over the adjacent side. We've seen how to break forces apart. We've seen how to put them together. Now let's look at some of the forces we'll need to deal with. In this course, we've already seen little arrows just saying, hey, I'm a force of 100 newtons. And you would draw that on your free body diagram of your object and start applying the equations that the sum of all the horizontal and vertical forces have to be 0. But there's some arrows we have to draw in ourselves. There's some other forces they can give us, and we have to work them out and add them. The first and most obvious to all of us, unless you're currently floating above your seat, is the weight. Any object feels a weight force acting through its centroid, the center of its shape, down. And this weight, sometimes called the force of gravity, is the mass times the acceleration due to gravity. Now, the acceleration due to gravity is 9.81 meters per second squared down. And sometimes it's useful to work these weights out at the start of the problem. For example, if you have a 100 kilogram mass and somewhere else you have a 50 kilogram mass in the problem, you know, there's not much point having to interrupt your calculations later to work those out. So sometimes it makes sense just, okay, the weight of this is the mass times the acceleration due to gravity. 100 times 9.81 is 981 newtons. And likewise, the weight of this is 50 kilograms times 9.81. Now I have a strong temptation to do that in my head, but I'm going to do it in my calculator because I'm an engineer and I want to get this right. So that's 490.5 newtons. I was right in my head, but the habit is more important to make sure you get it right the first time, every time. So you see, if you do those right at the start of the problem, those are some of the work already done and you've got it set aside and you can use it later. Now there's one thing to watch out for, is just whether they've given you the weight or this mass at the start of the problem. Because sometimes in a problem, they'll just say 100 Newton object. And it's far too easy. I've seen students do it just to go, oh, 100. That's the mass of the object. And then they find the weight by multiplying that by g. But no, this is 100 newtons. So that's already the weight. And so you don't need to multiply it by anything. In fact, if you wanted, you could then find the mass of the object. It's 100 newtons is the mass times 9.81. And so the mass of this object isn't 100 kilograms. In fact, it's 10.194 kilograms. So that's the one step you'd want to watch out for there. Another force we can meet is the spring force due to Hooke's law. Now the idea is a spring has a certain length it wants to be, an unstretched length, and it's sitting there beautifully in equilibrium. There is no spring force at all. If I stretch the spring, it wants to get back to its shorter length, so it'll exert a spring force pulling in at both ends. Now that's important. It pulls on both ends, not just one. Or if I squeeze it, it wants to push back out and get back to its original length. The equation for this spring force is minus k delta x. Now notice how that is meaningless gibberish. Just saying a bunch of letters and minuses doesn't mean anything. What I should say is the spring force is minus the spring constant times the change in length of the spring. Now the spring constant is just a measure of how strong the spring is. So for example, a 10 Newton per meter spring is much weaker than an 800 Newton per meter spring. And the change in length of the spring, well, anytime you see that little triangle, that's delta or change. And that's just the new value minus the old value. In this case, the change in length of the spring is the current length of the spring minus the unstretched length of the spring. Now, there's one important thing here. What's this minus? Well, this minus is what makes this what's called a restoring force. Why is it called restoring? Well, because whatever I do, it's trying to restore the original length of the spring. When I stretch it, making it longer, the force is trying to make it shorter, the opposite. Or if I squeezed it to be shorter, the force is in the opposite direction, trying to make it longer, because plus and minus are just directions in engineering. So a minus means this force is always opposite. So what effect does this have for me? Well, the two main effects are this minus direction It can often be simpler to get this from the diagram. So one thing I often do is I get the magnitude from the math. So I just find the size of the spring force by the spring constant times the change in length, and I get the direction from the diagram. Like, it is possible to keep all the pluses and minuses consistent and work them all out, but there's no points for showing off. Like, if I have a beam squeezing a spring down, and I'm told that beam is compressing the spring, well, I know if the spring is being made shorter, then the force is up. So I don't have to go through all of that. The other thing we have to watch out for is this change in length from the current and unstretched. This can often mean a bit of trigonometry and diagram work, where you have to draw the diagram and do some sines and coses, just like we used to break up the force into horizontal and component, or sine or cosine rules in order to find the original and new lengths of the springs in order to do that. What do I mean by that? Because you can't just throw around a thing like sine and cosine rule without saying it. If you have any triangle and you have three angles, A, B, C, and the opposite side lengths, A, B, and C, then you've got some rules that are always true and rarely but extremely useful in engineering. They don't come that often, but when they do come up, they save so much hassle. The first is the sine rule. The sine of angle A over side A is equal to the sine of angle B over side B. And if you want to go on, it's the same for C. So once you have a couple of sides and angles, you can work out the others. The other one is the cosine rule, which is side A squared is equal to side B squared plus C squared minus twice side B, side C times the cosine of angle A. And you might even recognize, hey, this looks a lot like Pythagoras, because if A was 90 degrees, this would disappear and leave Pythagoras. Now, these are things you see often at the start of terms in a little discussion of trigonometry, but people sort of ignore them because, you know, you're busy. It's like, oh, it's not the hard stuff yet. There's no such thing as easy or hard stuff in engineering. It's just whatever you're doing this week, and you should do it. So this sine and cosine rule, they can occasionally turn up for working out distances or angles you need. And one of the places they can turn up is a spring problem. If they give you some problem and they show you a spring has been pulled from point A to point B, and you draw it out, you might find a little bit of trigonometry helps you find the distances you need. Another force we look at is the tension. Now, the tension is the force in a rope or cable. And later we see it can also be in two force members. And the key points of this is it's always pulling. And it's always the same everywhere in the same rope. Now, what does that mean? Well, it means if I have some set of beams and girders connected together, connected by a rope, there'll be some tension in that rope, and it's always pulling, and it's the same everywhere. So if I look at point A and just that beam, I'll feel the force of tension pulling to the right. But if I look at point B on the other side, it will feel the same tension pulling in the direction of the rope. And wherever you look at a rope, it'll always be pulling with tension. And this can make quite a useful effect of the tension in a rope because it's how pulleys work. We'll have a quick look at one of those now. Bing! Behold, a diagram appears with the miracle of technology. We have a pulley and we have a rope going from an input force around this pulley system to hold up the mass M. And we are asked what input force is required to hold this system in equilibrium? Well, equilibrium is the magic keyword of any of these statics, which is the sum of all the forces is 0. And that immediately tells us something. In a nice equilibrium system like this, if we have an input force just pulling on a rope directly like this, then the input force is the tension on the rope. And you can prove that to yourself quite handily. If we were to just cut off this little bit of rope, we would see we have the input force pulling one way, the force of tension in the rope pulling in the opposite direction, and all the forces must add up to 0 in any axis, so the input force is equal to the tension. So we found the tension in the rope. Now we want to know what's required to hold this system in equilibrium. How do we do that? Well, there's only one other thing in the whole system to look at. We want to hold up this mass, M. And a mass means a weight. So we look at that mass being held up by the ropes. We draw a new diagram because if you try to do two things on one diagram, you end up doing neither of them very clearly. And in engineering, if you're not doing it clearly, you are not doing it at all. For examinations in the short term, but for co-workers, group work, legal investigations, approval, all that good stuff in the long term. So trust me, if you're in the habit of just doing messy work and thinking it'll be fine, it won't. So get over that. So we see here we have the weight, mass times acceleration due to gravity down. And now see up here, we have cut through the rope twice. So we have a tension pulling up and a tension pulling up. And when we look at this whole thing, the sum of all the vertical forces is 0 because we're in equilibrium, which means all the accelerations are 0. We've plus the tension up, minus the weight down is 0. So we've twice the tension minus the weight is 0. But we know the tension. We know that tension is the input force. And we rearrange, we find the input force is half of the weight of the block we're holding up. And that's the benefit of pulley systems like this. I'll clean up the diagram a bit so we can look at it fresh again. This technological stuff is nice. So we can see I'm applying an input force here to get a tension, but then because I have this rope looped around twice, I get that same tension twice holding that up. And if you'd more ropes, you'd be able to do even more. But the key point for the tension is it's the same tension everywhere in the rope, and it's always pulling in the direction of the rope.
I hope that was useful. There's plenty more videos in the playlist, but what's even more useful is lots of exam examples and exam specific advice. And that's what we do in the prep sessions. So join the Prep 101 Study Hub Facebook page to find out when those go on, and many of them are even free, so you definitely don't want to miss those. Hope to see you there.